There were a number of limitations to Bohr's model, and so as a result, scientists after Bohr started looking into the nature of electrons, and they discovered that electrons can actually act as particles and as waves. And so there are a number of scientists who led the way to what is now quantum mechanics, and we're going to look at 3 of them right now. The first scientist is de Broglie, and de Broglie noticed that matter can behave like a particle or a wave. Now, this is very contradictory, and it was difficult for scientists at the time to understand, and still for scientists to understand now. But the best way to think about this dual nature of matter acting either as a particle or a wave is to think about electrons. Now, when we're talking about the movement of electrons, we think about their energy, we think about their wavelength, and we think about their frequency. That is wave-like nature. So we're thinking about electrons as waves when we're talking about their energy, their wavelength, their frequency. When we're talking about protons and electrons and their interaction, we are thinking of electrons as particles. So that's just one way to help you to think about electrons not just as particles, but also as waves. De Broglie used this formula, wavelength equals h/mv, in order to relate wavelength to momentum, which is mass times velocity. So just to help you out, notice mass is on the bottom, velocity is not the same as frequency, velocity is the speed, but also notice that Planck's constant is used here. So we're using the work of other scientists in order to describe the wavelength of an object. Now notice, if we're talking about the dual nature of matter, that includes anything, including what we use on a daily basis. So the question becomes, well, do tennis balls act like waves? And the answer is yes, but not to the human eye. And the reason why we can't observe this nature is because tennis balls have such a large mass. So if you notice, since mass is so large, the wavelength is so small that it's not perceptible to the human eye. The next scientist who used de Broglie's work of the dual nature of matter was Heisenberg, and in his uncertainty principle, he noted that because of this dual nature of matter, it's impossible to know both the momentum and the location of an electron at the same time. And as a result of this uncertainty principle, Schrödinger came up with modern quantum mechanics, which I'm going to discuss right now. The first concept that we need to talk about is orbitals. Now, you should have learned about orbitals in your first year chemistry class, but just to refresh your memory, orbitals are regions of space around a nucleus where electrons are most likely to be found. There's the greatest probability of finding them. Now, each orbital has a unique shape and energy, which we will discuss in just a second. For you to note here, this diagram shows the electron density around a nucleus. Notice there is a small probability of finding electrons where that blue is extremely scarce, while when it becomes more dense of the blue color, the probability of finding an electron increases. And so what an orbital is just a region where there is a large probability of finding an electron. Notice for that diagram there, it kind of has a spherical shape, which we will look into in just one second. A couple of other terms for you to know. The principal quantum number is actually a term that Bohr utilized, talking about the first energy level, then the second, then the third, and thinking about electrons moving in orbits. Now, that's not the case, and we'll look at it in a second, but this concept relates to Bohr's model very well. Now, for you to know, an important fact is that as the number, your quantum number increases, so does the energy that the electrons have. The next term that we need to talk about is the electron shell. Now, the electron shell consists of orbitals that have the same principal quantum number. So, for example, if you have a 3s orbital, a 3d orbital, a 3p orbital, those are all part of the same electron shell. A subshell is an orbital or orbitals that have the same letter and the same number. So for example, 3d is one subshell, 3p is a different subshell. We're going to first talk about s orbitals. As you noticed in the previous slide, the electron densities create a shape that looks like a sphere, and all s orbitals have a spherical shape. If you notice though, the 1s orbital is smaller than the 2s, which is smaller than the 3s. So as the principal quantum number increases, the size of the subshell also increases. Now, a good way of understanding why that's the case is by looking at the radial probability distribution. If you notice in the diagram that's been provided, if you look at the 1s, which is on the far left-hand side, okay, the distance from the nucleus with the greatest probability is about 0.5 angstroms. Okay? If you look at the 2s, the region which has the greatest probability of having the electrons is actually 3 angstroms. So as you move from the 1s to the 2s, the location where you're most likely to find the electrons is farther away from the nucleus. One other thing for you to note, the 1s doesn't have a node. Notice the 2s and the 3s do. Nodes are areas where there is 0 probability of finding an electron. And so for the 1s, there's one region where there's a large probability of finding electrons. For the 2s, there are 2 regions. Obviously, the second hump there has a greater probability of having an electron than the first one, but the 2s also has a node, which is the region where you will not find electrons. The 3s has 3 humps where you are likely to find electrons. Obviously, the farthest one away from the nucleus is most likely to have the electrons. However, a 3s has 2 nodes. So, as your n increases, okay, there is also an increase in the most likely distance from the nucleus to find the electron, meaning you're more likely to find an electron farther away from the nucleus as your n increases. And we represent that by showing the subshells increasing in size as n increases. Here's the p orbital. We call that a dumbbell shape. Notice it's along the px, pz, and py axis. So there are 3 orbitals. There are 3 p orbitals, while for s there was only 1. For the d orbitals, notice all these different shapes. You will not be expected to draw these, but notice that there are 5 different orbitals where the electrons can be found. We're now going to be talking about writing electron configurations. We're going to go over the rules that you should have learned in your first year of chemistry, but let's go over them just to make sure we're on the same page. Your electron configuration, what it's doing is showing how electrons are going to be distributed in the orbitals of an atom. There are 3 principles that dictate how those electrons are distributed amongst the orbitals. The first is Aufbau's principle, which states that each electron must occupy the lowest energy orbital available. And I'll show you how the periodic table actually helps you to do that in just one second. The Pauli exclusion principle states that the maximum electrons that can occupy a single orbital is 2, but those 2 electrons must have opposite spins. The last principle is Hund's rule, which states that single electrons with the same spin must occupy degenerate orbitals before additional electrons with opposite spins can occupy the same orbital. We'll look at that when we work on orbital diagrams. Degenerate means having the same energy. The way that I write my electron configurations is that I actually use Pauli's exclusion principle in addition to the periodic table. Pauli's exclusion principle states that electrons occupy the lowest energy level first. And so, for example, if I were to write the electron configuration of nitrogen, which has an atomic number of 7, I start with hydrogen and I'm going to read the periodic table as if it were a book. So from left to right, from top to bottom. So I start off. The only other thing for you to know is that each box, for me, represents an electron. So I want to include hydrogen and helium in writing my electron configuration. Therefore, the electron configuration would be 1s2, because there are 2 electrons. Now, it's 1s because on the left-hand side, the 2 groups are s. Notice on this side, you have 2p 3p, 4p, and in the middle you have the 3d, 4d, 5d. So starting off, it would be 1s2 because there are two boxes. Helium is included in the 1s. Then it would be 2s2 because I have 2 electrons. Okay? And then if I'm going to stop off at nitrogen, I have 1, 2, 3. So it would be 2p3. One more example really quick to write the electron configuration of zinc. Okay, so I got to start off at the top. I have 1s2 because I'm including helium. Then I have 2s2, then 2p6, then 3s2, then 3p6 because I'm including all of these electrons, all the electrons along the 3p, then 4s2, and then I want to include all of the boxes in the 3d, so it would be 3d10 in order to write the electron configuration of zinc. We're going to do a practice problem, so we're going to write out the electron configuration of oxygen. Okay? For oxygen, it would be the electron configuration would be 1s2, then it would be 2s2 because I want to include beryllium, and then it would be 2p4 because I only go 4 boxes across in the 2p section. For the orbital diagram, I represent the orbitals with boxes. So keep in mind, 1s, the 1s subshell, only has one orbital. The 2s subshell also only has one orbital. And the 2p, remember there are 3 different orbitals for p, so it would be 3 boxes. For the orbital diagram, notice that I have my 1 box for my 1s, I have another 1 box for my 2s, and then I have 3 boxes for 2p because p has 3 orbitals. Now, according to the Pauli exclusion principle, you can only fit 2 electrons into each orbital, and they must have opposite spins. So if you notice for the 1s, it has 1 electron spinning in the upwards direction and then 1 spinning in the opposite direction. Same thing for the 2s. They have opposite spins. In order to figure out how to write the electrons for the 2p, you have to follow Hund's rule. Hund's rule states that electrons need to fill orbitals with the same spin first before you go back and you add electrons with opposite spins. So because I need 4 electrons in this 2p subshell, I must add 3 first, each with an upward spin, and then I can go back and fill that first box with the 4th electron, which has an opposite spin.